Okay, so this is a response to lesson 2.5, question number 5. So this is the problem that we have, and we are solving for x. So when you have a polynomial like this that you're trying to solve, typically we try to factor it. But this has 5 terms, which means we cannot factor it by grouping or using the methods that we've learned so far. So instead, we're going to have to start factoring it with synthetic division. But you don't want to just plug in any numbers. You want to plug in those values that are possible rational roots. So P represents the factors of the constant, which is 6. So the factors of 6 are positive and -1, positive or -2, positive or -3, and positive or -6. But your leading, and then Q represents your leading coefficient. Your leading coefficient is 2. The factors of 2 are positive or -1, along with positive or -2. So now you have to simplify this. You can't just leave this as your answer for your possible rational roots. You have to divide each of the possible factors of 6 by each factor of 2. So if we divide any of these numbers on the top by the 1, then that's just going to give you positive or -1, 2, 3, and 6, because anytime you divide by 1, you're just going to get back what you started with. But when you divide by 2, you're going to get a couple more interesting possible rational roots. So if you take the 1 divided by 2, 1 over 2 is 1/2. So that gives you a couple of more possible rational roots. 2 divided by 2 is just 1, so that is already on the list. But when you take 3 divided by 2, you get 3/2. So that's another possible, two more possible rational roots, because we have both the positive and the negative. So this now creates your entire list of possible rational roots. So now, again, I said I recommend that you start with just +1 and plugging it in your synthetic division. But before you plug it in synthetic division, you want to make sure that you have any missing term. You put zeros in for any missing terms. So you've got x to the 4th, 3rd, 2nd, x to the 1st, constant. So in this polynomial, we are not missing any terms. So if I substitute 1 into synthetic division and then take my coefficients 2, -1, 1, -2, and -6, and carry through with my synthetic division, I want to see if 1 is a solution of this polynomial, then the remainder will be 0. So bring this down, multiply, you get 2, add, we get 1. 1 times 1 is 1. Add, you get 2. 2 times 1 is 2. Add, we get 0. 1 times 0 is 0. And then we get -6. So this does not give us 0. So 1 is not going to work. So then we have to try -1, or we could have just erased all of this and kind of started again with -1. So try to see if -1 is a solution. So again, we've got coefficients of 2, -1, 1, -2, and -6. But this time I'm substituting -1 into my synthetic division. Carry down your leading coefficient. That one stays the same. 2 times -1 is -2. When I add, I get -3. Multiply -1 times -3, I get a +3. 1 plus 3 becomes 4. 4 times -1 is -4. -2 times -2 plus -4 is a -6. And then -1 times -6 is +6, which then gives us a remainder of 0. So what does that tell us? That means our actual solutions, or actual roots, will include 1. So, or -1, sorry. So -1 is one of the roots. but it's not all of them. There should be 4. The polynomial has a degree of 4, which means there should be 4 solutions, and we have to find all of them. But rather than continuing to use synthetic division over and over again, you want to look at your new numbers here. So the -1 does tell us that the polynomial has a factor of x plus 1. And then these numbers here tell us what the remaining polynomial is. So when I divide this polynomial by x plus 1, I get these coefficients. Since I had divided an x to the 4th, the 2 now is going to be an x to the 3rd term. The -3 is going to be your x squared, coefficient for x squared. The 4 is your coefficient for x. Your -6 is now your new constant. So at this point, we have 4 terms. When you have 4 terms, you always try to see if it can be factored by grouping. If it can, that's great, but it doesn't always, it's not always possible. But it just so happens that this polynomial can be factored by grouping. So when I cut it in half, the first 2 terms I can factor out an x squared, leaving me with 2x minus 3. In my second 2 terms, I can factor out a positive 2, which then, again, when I divide both of those terms by 2, gives me 2x minus 3. All that in parentheses. So now I have a 2x minus 3 in common. So think of this as one term, think of this as one term. Since they have the 2x minus 3 in common, you can factor that out and then put the x squared plus 2 together in its own set of parentheses and bring down this x plus 1. So now that we've factored this completely, the x squared plus 2 cannot be factored anymore. It's now time to set each factor equal to 0 and solve. So when I take the x plus 1 and set it equal to 0, subtract 1, and I get x equals, 0. 0 minus 1 then will be -1, which is the solution that I've already written down. But then I also have a factor of 2x minus 3. So when I set that equal to 0, add 3 to both sides. And that gives me 2x equals 3, divide by 2, and x equals then 3/2. So that's my second solution. And then the x squared plus 2, when I set that equal to 0, again, get the x squared by itself. But this one's going to be special. Because it's x squared, you need to take the square root of both sides. So when I take the square root of the x squared, that will give me x. But because it's a square root, there's going to be 2 solutions, the positive and the negative. Now, because you have a negative under the radical, I would recommend that you factor this into square root of 2 and square root of -1. The square root of 2 cannot be simplified because 2 is not a perfect square. And the square root of -1, though, can. That becomes your I. So that's where that I comes from. So these are imaginary solutions. They are not graphable. They are called complex solutions. But now you can see all 4 of your solutions.